All right, so this is section 10.2, day 2, video number 3. This one will complete our trilogy for 10.2, day 2. We're going to have the three examples that are left. We have discussed at this point how to calculate speed, the basic idea of vectors, position, velocity, acceleration, and so on. So we're just doing some more examples. Example number 7 here says a particle moves along the graph of y equals x squared plus x, with its x coordinate changing at a rate of dx over dt equals 2 over t cubed, for t is greater than 0. If x of 1 equals 1, find the particle's position at t equals 2, and find the speed of the particle at t equals 2. So we got a couple of different things we have to do here. We are given, I would say, a decent amount of information, not obviously everything that we need. We're going to have to piece a bunch of things together here. All right, we are given how x changes. We are given a function of y in terms of x. We are not, however, given how y changes with respect to t. In order to do that, we're going to have to piece some things together because we're going to need dy over dt in order to find speed, specifically at time t equals 2. In order to find the particle's position, we're also going to need some additional information. So let's set up what we know. We know that in general, dy over dx, because this is parametric, is dy over dt over dx over dt. Well, they gave us dx over dt. We can actually fill that in. They did not give us dy over dt. They did not give us dy over dx. However, we can find dy over dx because we are given y in terms of x right there. So let's go ahead and plug a couple of these things in. First of all, dy dx, that's the derivative of y with respect to x. That's just going to be 2x plus 1. We don't know dy over dt, but we do know dx over dt is 2 over t cubed. So to solve for dy over dt, we're going to go ahead and multiply both sides of that equation by 2 over t cubed. So we'll get 2 over t cubed times 2x plus 1. That is dy over dt. However, we're going to want to put that all into terms of t. Well, the problem is we need to find an expression of x itself in terms of t. Well, the good news is they have given us that dx over dt is 2 over t cubed. And they've given me an initial condition that x of 1 is 1. So basically, when t equals 1, x equals 1. So that's an initial condition. So now we can use separable differential equations here to be able to solve this. So let's go ahead and do that. We'll multiply both sides by dt, and we get that dx is, I'm going to rewrite that as 2t to the negative 3 power dt. So we're going to go ahead and take antiderivatives now on both sides of the equation, and we get, actually I'll just write these out as integrals, we can do that. So the antiderivative on the left to complete that integral is just going to be x. The antiderivative on the right, raise the exponent by 1, so we get t to the negative 2. Dividing the coefficient by negative 2, we get negative 1, so we get a negative out front, and don't forget our plus c. We can now use our initial condition that t equals 1 and x equals 1 to find c. So I'm going to go ahead and plug in 1 for x. If I plug in 1 for t, 1 to the negative 2 is still 1, but it's going to make it a negative 1 because of that negative out front. So to solve for c, we'll just add the 1 to both sides, and we get that c equals 2. Which means that we have the equation x equals negative t to the negative 2 plus 2, which is, I guess if we rewrite that just a slightly better form, negative 1 over t squared plus 2. So now I have an expression for x in terms of t only. So I can take all of this and plug it in for x. And then we'll have y with respect to t, or the derivative of y with respect to t, all in terms of t. So let's go ahead and do that. Now we get 2 over t cubed times 2 times negative 1 over t squared plus 2. Don't forget the extra plus 1. That is dy over dt. So now I have dy over dt in terms of t. I have dx over dt in terms of t because they gave that to us. So now we should be able to find the speed. Remember that speed is the square root of dx over dt squared plus dy over dt squared. And if I want to find that specific speed at the time t equals 2, I'm just going to plug in 2 for both of the t's. So we're going to get the speed at time t equals 2. If we plug in 2 into dx over dt, which was 2 over t cubed, that's going to be 2 over 2 cubed, 2 over 8, so that's 1/4 squared. And then if I plug 2 into my dy over dt, let's see here. Can we do this all mentally? Probably. If I plug 2 into the 1 over t squared on the inner parentheses there, I'm going to get, what is that, 1/4. 1/4 plus 2 is going to be 9/4 times 2 is 18/4 plus 1, and fourths is 22/4. That reduces, though. That's a lot of stuff here. Can be done by hand, so let's see. All right, just trust me in this case that it does work out to be 9 over 8 when you plug it all in. You can write this off on the side. I'm just trying to conserve a little bit of space. But you do need to plug in 2 for all your t's, and it does reduce to 9 over 8 squared. So that would be the speed. Now that's the exact speed. That is not going to work out to be a nice number. So if you want to get a decimal approximation that means something, it would be about 1.152. If it asks for the exact answer, that one right there is perfectly fine. You don't have to do any further simplifications because I don't think that works out nicely. Obviously it doesn't. It's 1.152. All right, so that's our speed at time t equals 2. So I kind of answered this part first. Whoops. Kind of answered this part right here first. Now we need to go back and we still need to find the particle's position at time t equals 2. Well, we can find the x value of the position pretty easily because I have the x coordinate right here. Just got to plug in 2. So I know that x at 2 is going to be negative 1 over plugging in a 2 into the t. It's 4 plus 2. So negative 1/4 and 2. 2 in terms of fourths is 8/4. So that's going to be 7/4. And then to find the y position, well, I have x at time t equals 2. Why can't I just plug that into here and find the y value when x is 7/4? Probably the easiest thing to do. So y at 2 is going to be 7/4 squared plus another 7/4. So let's see, what's that going to be? That's going to be 49/16 plus 7/4 in terms of 16ths. We'll multiply the top and the bottom by 4 is 28/16. So 49 and 28 is going to be 77/16, I believe. Yes, 77/16. So now we have our y value at time t equals 2. So our position at time t equals 2. Remember, you can either use S or R because that's typically what they use. I think it's S usually in the book, even though R is more appropriate. We use S. S of 2 is going to be 7/4, 77/16. And that is an exact value. All right, that is definitely the longest of these remaining problems. But we have found the speed and the position at time t equals 2. All right, example number 8. A particle moves along a curve with its position vector given by, and again, these are horrible notations because those should be angled brackets. 3 cosine of t over 2, 5 sine of t over 4, for t is greater than or equal to 0. Find the acceleration vector when the particle is at rest for the first time. So we're given the position vector. We can find the acceleration vector just by taking derivatives. So let's do that part first, and then we'll have to figure out what time we have to plug in. So we have to get the velocity vector, which is the derivative of each component of the position vector. So the derivative of 3 cosine of t over 2. Remember that that's basically the same thing as saying 3 cosine of 1/2 t. It might be easier to see it in that form. It's still a chain rule, so we have to do the derivative of cosine, which is going to be negative sine, so we'll have a negative sine. It's still going to be of 1/2 t times the derivative of the inside, which is 1/2. Got to multiply the half by the 3 coefficient that was already there, so we should have 3/2. Okay, that's the x component. The y component, similar idea. The derivative of sine is cosine, and I'll write that as 1/4 t. Times the derivative of the inside, the 1/4 times the coefficient on the outside gives us 5/4. There's our velocity, and our acceleration vector is now the derivative of that. Same general idea. So the first one, the derivative of sine is cosine, so it'll still be negative cosine 1/2 t. The 1/2 times the 3/2 on the outside gives us a 3/4. Derivative of cosine is negative sine 1/4 t. 1/4 times the 5/4 will give us 5/16. There is our acceleration vector in terms of t. What we need to do is we need to figure out what the acceleration vector is the first time the particle is at rest. For a particle to be at rest, that means that the velocity has to equal 0. Well, for the velocity to equal 0, we need to have no movement in either the x or the y direction. So we need to set each of the components of the velocity equal to 0 and solve. So let's do that. We need to know when the velocity equals 0. So that's when negative 3/2 sine of 1/2 t equals 0, and when 5/4 cosine of 1/4 t also equals 0. And these two things have to match, so the t values have to be the same. So we'll figure out when the first time is. Remember, this is when t is greater than or equal to 0, so we're not concerned with any kind of negative angles here. So the first thing we do on the sine part, we'll divide both sides by negative 3/2. Dividing 0 by that is still 0, so we get that sine of 1/2 t is still 0. So we need to know when the angle 1/2 t equals the values that give you sine equals 0. Well, sine is going to be 0 at 0, pi, 2 pi, and so on. But we're not solving for 1/2 t, we are solving for t. So let's multiply both sides by 2, and we'll get that our t values are 0, 2 pi, 4 pi, and so on. Hopefully one of those values will work. Same idea with cosine. Divide both sides by 5/4. We still get 0 on the right. So we get that cosine of 1/4 t is 0. We need to know when 1/4 of t equals the angles of cosine that give us 0, or the angles of cosine are all of the odd pi halves. So that's going to be pi halves, 3 pi halves, 5 pi halves, and so on. So we got to solve for t by multiplying everything by 4. So t, let's see, multiplying pi over 2 by 4 gives you 2 pi. And then the next one's going to be 6 pi. I don't really need to worry about the rest of them. because 2 pi is the first time when time is greater than or equal to 0 that this occurs. So we now need to plug in 2 pi into our acceleration, and we will have our acceleration vector at the first time the particle is at rest. So we're going to do the acceleration at 2 pi, which is -3/4 cosine of, plugging in 2 pi, we're going to get cosine of pi, and then -5/16 sine of, plugging in 2 pi there, we're going to get, it looks like pi over 2, reducing 1/4 of 2 pi. So simplifying all of that, cosine of pi is -1, so that's going to give us +3/4. And sine of pi halves is 1, so we're going to get -5/16. So that's the acceleration vector at the first moment that this particle is at rest. All right, one more example to go. Kind of a cool one, only because of the fact that I like roller coasters, so kind of a neat little thing here. So a roller coaster track has an inverted loop as a portion of its course. Okay, basically that just means it goes upside down. The position of the car on the track in feet at time t seconds from 0 to 7 is given by the equations x equals that equation, y equals that equation. I'm not reading those out. When is the car at the top of the loop, and what is its speed at that time? So we want to know when the car reaches the top of the loop, so what time that is, and then what the speed is at that particular time. So the speed part, we're going to do our dx over dt and dy over dt and plug in the time, but we have to find the first time that this thing is at the top of the loop. If we want to figure out the first time this thing is at the top of the loop, what we're trying to figure out is a maximum, because we are trying to find out the maximum y value. Okay, that should make sense because y is your up and down, it's your vertical position. So we want to maximize our y value. So if you go back to the idea of max and mins, we're going to take dy over dt. Let's see, dy over dt is going to be -12 cosine of t plus 2. Oops, excuse me, sine of t plus 2. Right, derivative of cosine is negative sine. And then the chain rule just gives us a 1 on the inside, so we don't have to worry about multiplying by anything additional. And we need to set that equal to 0, because we need to maximize this thing. So we need to find out its max. So let's find the critical values first. Divide both sides by -12. We get that sine of t plus 2 is 0. So we need t plus 2 to equal all the values that give us sine of 0. So 0, pi, 2 pi, 3 pi, and so on. Now, we don't need to worry about certain of these values. I'll explain that in a second. Let's go ahead and solve for t. So t is going to be, by subtracting 2 on both sides, we get -2, pi minus 2, 2 pi minus 2, 3 pi minus 2, and so on. Remember that our domain is limited here from 0 to 7. So we only need to worry about values of t that give us something in between 0 and 7. Well, -2 is out. Pi is approximately 3.14, so 3.14 minus 2, that's between 0 and 7. 2 pi is about 6.28. 6.28 minus 2 is still between 0 and 7. 3 pi is about, I don't know, it's a little bit under 9.5. 9.5 minus 2 is going to be greater than 7, so anything past that is out of the possibility. So we've really only got 2 possibilities. We can go back to an old school sign chart and figure out which one of these gives us a max, which one of them gives us a min. There are other ways to do this, but this is probably just the easiest one that I can think of right now. So if we do pi minus 2 and 2 pi minus 2, we can just do our old-fashioned sign chart, plug values back in, and see what we get. So I can use 0 and 7 since those are not critical values. Those will make things a little bit easier, at least I think it will, maybe not. Yeah, let's go ahead and use 0. So if I plug 0 in for t right here, I'm taking the sine of 2. Well, you kind of have to know your estimations here, especially if you have to do this without a calculator. Sine of 2, 2 is a number that is in between 0 and pi for sure. So anything where sine is in between 0 and pi is positive, but you got to multiply it by the negative 12 on the outside. So that gives you a negative value here, which means that your function is decreasing. Something in between pi minus 2 and 2 pi minus 2. Well, I guess, let's see, pi minus 2 and 2 pi minus 2. I would guess pi is going to work. If you plug pi in, you're going to get pi plus 2, which gives you a negative value for sine, but then that negative times the negative 12 out on the outside gives you a positive, so now it's increasing there. And then if we pick 7, sine of 9, it's a little bit harder because it's well past one circle, but it actually brings you back into the first and second quadrant, which makes this whole thing negative again. So your maximum is at 2 pi minus 2. So the time is going to be at 2 pi minus 2 when the roller coaster has reached its highest or top of the loop. Okay, it didn't ask us to like specifically state like what the highest part is. You could figure that out, but we're not worried about that right now. So that's when the car is at the top of the loop. Now we want to know what the speed is at that particular time. So to do that, we also need dx over dt, which is, according to this, 5 minus 12 cosine of t plus 2. Again, the chain rule is only going to give you a 1 to multiply, so we're good there. So we have to basically plug in 2 pi minus 2 into each one of those, square it, add them together, take the square root to find our speed. So our speed is going to be, if we plug in 2 pi minus 2 into here, you're going to get 2 pi minus 2 plus 2 on the inside, which is just 2 pi. So you have to take the cosine of 2 pi, which is 1. So you get 5 minus 12, which is negative 7. So we'll get negative 7 squared. And I should write, this is the speed evaluated when t equals 2 pi minus 2. And then we'll add that, plugging a 2 pi minus 2 into here. Once again, I just get 2 pi on the inside of the parentheses. Sine of 2 pi is 0. So what we ultimately get here is the square root of negative 7 squared, which is 49. Take the square root, and you get 7 feet per second. Is that what it is? Yeah, per second. So this thing has a speed of 7 feet per second when it is at the very top of the loop. All right, that is plenty enough. That's definitely by far the longest video. So hopefully you have plenty enough to finish up 10.2, and good luck.